much, Ricardo. Thank you very much, everyone, for coming. Thank you, first of all, for inviting me. It's really a pleasure and an honor to be here. And I really hope that the current world situation will allow me to travel very soon to Brazil and see everyone in person. All right, I'm gonna start by introducing a bit of what initiated this study of fold products of linear forms and ideals generated by fold products of linear forms. And everything started from coding theory. So I'll be very succinct with very brief with this coding theory part, but there are some gadgets that, of course, we will keep in mind as we move along with concepts and the results. So linear code, we start with any field, and a linear code is just the image of a linear map. Elements of linear code are called code words, and every linear map comes with a matrix. Well, comes with several, but if we use standard basis, usually people like to use standard basis in the domain and the codomain, and we get a matrix that's called the generating matrix. I assume that the rank, of course, n is bigger than k, and I assume that the rank of G is k, so that's an injective map. And also for the sake of this talk and of the topic of this talk, we assume that this matrix has no zero columns. Usually in coding theory, it may happen that they have zero columns, these matrices. N is called the length, K, which we know already, is called the dimension. For some particular codes where linear codes where the map is not is defined by other means and is not a one-to-one, finding the dimension, finding the rank of this generating matrix also becomes an interesting algebraic commutative problem. Usually you want to find the Hilbert function. I'm thinking here about evaluation codes, and you want to find the Hilbert function of ideal of points, Hilbert function at value k. All right. So those are pretty much standard parameters. They are called parameters. One of the most, maybe the most important gadget or parameter coming to for a linear code is what's called the minimum distance, which is basically the smallest number or minimum number of non-zero entries in a element of in a code word that's not the zero code word, right? And here is why it's useful in practice. With this minimum distance, we can detect d-1 errors in the message. So this linear code and codes in general are used to first to encode, that means to translate some information into different information that can be sent then back to some to a different point where it's decoded back to the original message. Well, when we send this message, that channel, which can be, airwaves or satellite or even, have a CD and you play it, and so that's channel might introduce errors. So and it's good to know how can we detect errors so that the message we receive it's it's reliable, and also if we can correct them. And this is where the minimum distance come into play. To my knowledge, for linear codes, there is no other gadget that can help with this error correction problem. So minimum distance is super important. Now, I'm not going to go into the definition. We can define a generalized Hamming weight of a linear code, and for each R, from 1 all the way to K, the dimension. And the way we define this, we have that D1 is actually the minimum distance that we saw above. And this is, if you want to forget about everything and you can define the minimum distance, the R's generalized Hamming weight, to be n minus the maximum number of columns of that generating matrix G. So those columns should span a K minus R dimensional vector space. So we're going to use this result in the future. So back in 1999, the Bohr and Pelikan observed a very obvious thing. The weight of a vector is less or equal than m if and only if all distinct n+1 products of its entries vanish. Right, so I have here an example, and you see the weight is 3 because if we take any 4 entries in that vector v, it might contain a 0, so their product is 0, and there is a product of 3 entries that is different than 0. So now translating this back to our linear codes. So we have to look for weights of code words, right? But every code word is the image of that linear map. So it's another vector times the generating matrix. And now we can translate this operation of product here into a more pleasant form or shape. To the jth column, we create this linear form that has as coefficients the entries in that column. So if we do this product of vector times matrix, means that we do in every entry j, we evaluate that linear form at this point d. Right, so, and now we want to look at how many non-zero entries, what's the weight of this code word C. So basically we look at all products, all those n+1 products of all these linear forms, and they should have a solution, that point D, common solution. So we can translate now the problem of finding minimum distance as the maximum integer E, such that those E-fold products has only the trivial solution. Right, so And now that was the starting point of considering the ideal generated by A-fold products of linear forms. So I look at all the linear forms dual to the columns of the generated matrix G. I do all those products, A products, and they will generate an ideal that will be called ideal generated by A-fold products of linear forms that are defining C. And now, what does it mean for E, for to have the trivial solution? Means the trivial solution has coordinates 0, 0, 0, right? So the minimum distance D is the maximum integer E such that the radical of this ideal of E-fold products of linear forms is the maximal ideal. Now, if we want to think projectively, and this is what we like to do, and I like to do a lot. So 0, 0, 0 is not a valid point in the projective space. So that variety with defined by those E-fold products should be empty. And this is another way to characterize that we get the radical is this maximal ideal, which is the trivial maximal ideal, is that the height of this ideal is precisely K, is the maximum value that can have. So now, so this was the how is all these ideals came to life, and of course you have some ideals, and you have a nice connection between some commutative algebraic invariant, which is the height, and the minimum distance of a linear code. So it's a very cool way to view very applicable things in terms of abstract algebra. And now we want to see, okay, these ideals, do they have more properties? And this is what I'm gonna talk about next. So we start with a bunch of linear forms. Some possibly are proportional, and such that they generate the trivial maximal ideal in this in the ring of homogeneous polynomials with coefficients in K. And then consider the ideal generated by A-fold products of those linear forms. So here is an example. The coefficients, you see, I put them also as columns, so we'll make the connection with linear codes. And now let's let's do some calculations. F is the product of all linear forms. So if we look at 5-fold products, that means we take all 5 products of the entries. Well, we have 5 of them, so there's just this product, which is F. And the height of this ideal is 1. It's a principal ideal. Now, this is an easier way to write all the 4 products and fit in a slide. So I4 is generated by all 4th product. So first one is F over X1, means X2 times X3 times X1 minus X2 times X1 minus X3, and so forth. The height is 2. We use any computer program that we prefer to calculate this. Similar, I3 has height 2, I2, we see that has height 3, and I1 is actually the ideal generated by each individual linear form. So that's the irrelevant maximal ideal, as height 3. So even from this, we see that 2 is the maximum value for each. Here should be, it's a typo, it should be a 1. 2 is the maximum value when the height of these ideals is 3, because then when we go up to A being 3, we drop the height to 2, right? So that will tell us that the minimum distance is 2 by what we discussed before. Now let's use the result. So D0 should be, we have 5 columns, and what's the maximum number of these columns that will span a 3 minus 0 dimensional vector space? Well, all 3 will span, because rank is 3, so all 5 will span that dimension 3. So this is 5 minus 5 is 0. D1, which is minimum distance, so it will be 5 minus, what's the maximum number of columns that will span a 3 minus 1, right? This one, 3 minus 1 dimensional, which is 2 vector space. Well, we have first, second, and fourth columns, they will span a 2-dimensional vector space. Or let's see, first, third, and the fifth also span a 2-dimensional vector space. And there is no other, all the other will be like 2 columns. So the maximum number we are looking here is 3. So 5 minus 3 is 2, which matches with what we discovered before. D2, so how many was the maximum number of columns that will span a 1-dimensional vector space? 3 minus 2 is 1, right? So each column, and we don't have proportional columns to, so the maximum number is 1, so D2 is 4. D3, similar argument, you can figure out that there is no column that spans a 0-dimensional vector space. We don't have 0 columns, right? So that will be, D3 is 5. So we have a result that says that the height, if A, our from A fold products, if A is between dr plus 1 and dr, sorry, plus 1 and dr plus 1, then the height is exactly k minus r. And please contact Ricardo if you want to for these slides. I would really like to share them. So we don't have time to check this right now, but right, so if r is 0, so if A is between 1 and D1, so between 1 and 2, the height should be 3 minus 0. Yes, indeed, we have a height 3 here, height 3 here. If A is between, let's make r equal 1, so D1 plus 1, so that's 2 plus 1, 3, and D2, which is 4, so A is between 3 and 4, the height should be 3 minus 1, which is 2. So indeed, we have 2, 2 here. And similar for the other one. Okay, I said that we're not going to check, but check. When we have a matrix the columns, we can build a matroid, which is a very strong combinatorial gadget. And to this matroid, we associate what is called the tot polynomial. This is actually the results. This is classical. I'm not attributing this to my work with Ben and Mehdi in 2006. So we use in that paper, we use this tot polynomial to obtain the following commutative algebraic information. So the degree, which if we have a variety, or the degree, you slice the variety with enough hyperplanes until you get to a zero-dimensional object, which will mean a number of points. And that number of points that we get is exactly the degree. So let me go to the board. I'll stop share, and I hope you can see me or pin my image. Right, so if we have a curve like this, the degree, we slice it with a general line, right? It's general, so will not be tangent or anything. So the degree of this is 1, 2, 3, 4. Right, so it's a quartic. All right, I'll go back to sharing. And we can capture also the degree from the leading coefficients of the Hilbert polynomial of the ring, coordinate ring. So we have this connection. This is the result that Ben, Mehdi, and I showed, and also we showed the minimum number of generators comes with this formula. And I will not go through all the examples. So I did the calculations. The tot polynomial is not hard to compute. At the end, if we have time, I can show you how to do this for this example. So anyway, we got this, and then P0 is the maximum. Let's look here, maximum value, maximum J, such that the coefficient 0J is different than 0. So that means coefficient of x to the 0, y to the j. So the coefficient is P0 is 2, right? Right here. Not coefficient. P0 is 2 because the coefficient one second, let me. So we have a y squared right here. P1 is the maximum j such that coefficient C1, so x, where will x show up? So we have a xy to the 1. If we have had xy squared somewhere, then the P1 should be 2, right? And so forth. And those are the values. And now we use this formula. I mean, not. So we identify who is J, who is 1, who is R, and we get the degree is indeed 5 because I5 is generated by the product of all linear forms. And we have 5 of them, and the minimum number of generators is actually 1 because it's just one generator. So we do this for all the other and we'll see that things match as they are supposed to match. Like, for example, the last one, remember I1 is the maximal ideal, so the degree is 1, and is generated by the variables, and we have 3 minimally generated by the variable. We have 3 variables, so things are correct. Now the next part, and now we get to the work that Ricardo and you and I did very recently. So the next thing important in commutative algebra is primary decomposition. First thing, when we look at primary decomposition, we look at minimal prime, and the minimal prime are prime ideal primes generated by n minus a plus 1 of those linear forms. And the argument to do this is fairly simple. So we want the product L1, LA to be in our prime P. So one of them should be in P. So L1 is in P. Then we move to another generator that doesn't contain L1, let's say L2 all the way to LA plus 1. That's also in our prime P that contains I sub A. So one of those factors should be in P. Let's say it's L2. L2 might be equal to L1, right? We allow repetitions, right? So that doesn't matter. We count it separately to get to this formula. So we get that indeed we have n minus a plus 1 linear forms in our prime P. And now we know that any ideal generated by linear forms is prime. So those P should be equal to this ideal that I highlighted. So this is how we get the minimal primes. But of course, and it's often the case, we have also embedded primes, so or primes that are not minimal. Now here is the connection of these ideals generated by A-fold products of linear forms with more classical and concepts called star configurations, or defining ideals of star configurations. And we'll see where the connection lies. So we start with a hyperplane arrangement, and we assume that's generic. That means any k of those of the defining linear forms are linearly independent. This is a very special type of hyperplane arrangement. All right, so and then the codimension C star configuration associated to this hyperplane arrangement is the union of all those intersections of hyperplanes. If we translate this into defining ideals, the ideal defining a codimension C star configuration is the intersection of all those linear primes. And here is the connection. The defining ideal of the codimension C star configuration is actually the n minus C plus 1, the ideal generated by n minus C plus 1 fold products of linear forms that define that hyperplane arrangement. So now for this special case, we have a primary decomposition, right? And actually these are the minimal primes. This will be This is one of the special cases when the all the associated primes are minimal. Now, star configuration, they correspond to something very interesting in coding theory. And we say that a linear code is maximum distance separable code if and only if the minimum distance is as maximum as possible. So we have in general the singleton bound that says that D is less or equal than n minus k plus 1. Well, an MDS code has D equal to that upper bound. So now let's, so the maximum number of columns of G that span a k minus 1 dimensional vector space is n minus this D, which equals k minus 1. So that means that any columns of G are linearly independent. Any k columns. Well, that's exactly that any k of the linear forms dual to the columns of G are linearly independent, which is exactly that hyperplanar arrangement that defines, that helps defining a star configuration. Also, we have the, in this particular case, every time, once we go up to like, so D1 plus 1, D1 plus 2, and so forth. So as we move one step further, we'll get precisely the next generalized Hamming weight. So D1 plus 1 will be actually equal to D2. D2 plus 1 will be actually equal to D3 and so forth because of this. So these are very special linear codes. So let's conclude. So in the case, now talking about primary decomposition, we've seen via this connection with star configuration, we've seen that the primary decomposition of A-fold product of the ideal generated by A-fold products of linear form when A is between this range, sorry, D plus 1 and N is exactly this. It's a very nice primary decomposition. So now in general case, I showed in 2010 that every time we are between the other range, doesn't matter what kind of linear code we have, any linear code, if A is between 1 and the minimum distance, always get the power of the maximal irrelevant ideal. So not only the height is the maximum as possible, we get that the ideal itself is a power of the irrelevant ideal, maximal ideal. And now here is the one of the main results of our work. So we have any collection of linear forms, and we create this set of all linear primes generated by subsets of C. So we take any subset of C, those are subsets of linear forms, so they will generate prime ideals. Then the primary decomposition looks like this. And where this number nu of P is the number of elements of C counted with multiplicity that belong to that particular P that we choose in that intersection. So this is a nice structure theorem. Of course, it includes all our special cases like this one and this one. So So for example, the first one with MDS code. So we take a prime ideal that's different, the irrelevant ideal in that set of primes, and we want IA, our ideal, to be included in P. So let's say the height of our prime is C, which is because P is different than the irrelevant maximum ideal, is less than K or equal than K minus 1. We also know that P is generated by at least n minus a plus 1 elements of C and of big calligraphic C. Now, if C is MDS, then that means all the linear primes that belong to, all the linear forms that belong to P, they cannot have any linear dependence between them, because we know that any K of them are linearly independent. And since the height is less or equal than K minus 1, so we can have exactly C elements, little c elements in P. So, and that will make C is n minus a plus 1, and that number that shows as exponent here is 1. So therefore, we get exactly this part over here for this big parenthesis. And now this is also saturated ideal. So this is like everything here is included in M to the A, because IA equals its saturation. So, and IA is included in M to the A, because IA is generated by product of A linear forms, right? So then I'll show why my result from 2010 works also in our general theorem. So for the example, I look at two special cases, and I'm gonna go, I'm running out of time. So we get this primary decomposition for I3, and for I4, we get this primary decomposition. Again, if you want to see the details, I can share with no problems these slides. We can talk after. Now, also we have an important result that tells us about the graded free resolution of these ideals. Basically, in this paragraph, I explain what's a free resolution. So basically, we want to see how far is a finally generated R model from being free. And this is one way is to have this free resolution. So this is how we do this. Say M is generated by N1 elements, so we have naturally we have a surjective map from R to the N1 into M. Now this one has a kernel, and the kernel is a submodule of this free module. So it's finitely generated and has, they say, has N2 generators, minimal generators. So therefore we can create this map, and we have this composition It's because the image is included in the kernel and actually be equal. We want this to be an exact complex. So this composition is 0. And so this is how you do it. Now we are talking here about homogeneous polynomials. So we have grading, standard grading, like given by the degree. So often in our calculations, we want to keep track of this. So, and that's when we obtain graded free resolutions. And we say that a homogeneous ideal generated in degree A is linearly graded free resolution. It has free resolution of this form. So let me explain to you. So A has N1 generators of degree A, minimal generators. And then this is saying that there are some linear relations among these generators. So that one tells us that there are relations among these generators with linear coefficients, linear forms as coefficients, and we have N2, many of them. Then we do another, the next one will be minus A plus 2, and 2 minus 1 is 1. So we have, again, relations among those relations with linear coefficient and so forth. By Hilbert-Syzygy theorem, we must stop because this is a Noetherian ring, and it's a ring of polynomials. So wherever we stop, we get there is also some called projective dimension or homological dimension that it's actually, yes, it's B. So that number B is also important. So now some observations about this linear graded free resolution. So we'll be interested to find those Betti numbers or graded Betti numbers and one, so those exponents, and then have an understanding of the projective dimension. For the case of star configuration, Geramita, Harbo, Migliore, they show 2 is B, and they present the formula for NIs and show that indeed we have a linear graded free resolution. Oh, did I forget to? Okay, I'm sorry, I skipped. So the main result is this one of Ricardo, you, and I. Any ideal generated by F-fold product of linear form has a linear graded free resolution. That's a very important result. And now this was generalizes the result of Geramita, Harbo, Migliore. Also, in that situation, when A is between 1 and D, we know that I sub A is a power of the irrelevant maximal ideal. B is K minus 1, and the formulas for NIs are known. For K equal 2, again, so only in 2 variables, we can get the information that we want. In our example, these are the linear graded free resolution that we get. And so current project of Ricardo and you and I is to figure out these Betti numbers that at this moment we don't have any formula for them. This when A is n minus 1, this is known already. So maybe I should. All right, so the last couple of minutes, I want to talk about another part of these ideas and how we connect them with classical gadgets. So special fibers. If one has a homogeneous idea, let's say, is generated, not necessarily minimally, and we'll see that we'll not consider minimal generators. You saw how it's kind of hard to find the minimum number of generators of ideal generated by A-fold products of linear form. So rather than trying to find that, let's work with all of them. We just get some, redundant factors or redundant generators in these special fibers. So the question is, what are the equations? So we can make a nice rational map. And what are the equations of the image? And there will be homogeneous polynomials in the new variables y1, ym that we choose for our codomain. Or if in a more algebraic way, so what are the pure relations between these generators, right? So with only constant coefficients, that's what we are looking. So in example, because we have this relation, so first linear form minus the second equals this one was the fourth, right? So we have this relation. So we multiply this with f squared over the product of x1, x2, and x1 minus x2, the product of these three forms. And now we distribute, so we have f squared over this, x2 times x1 minus x2 minus f squared over x1 times x1 minus x2 minus f squared. And we see that that's exactly, so we get this generator, this relation between the y's, the new variable, y2, y4 minus y1, y4 minus y1, y2. Similarly, for the other dependence, x1 minus x3 minus x1 minus x3, we get that. And also we have this relations, this between four of the linear forms. But if we calculate, we see that y2, y4, g2 minus y3, y5, g1 is y1, g. And we know that the defining ideal of this special fiber is a prime ideal. So g is in this ideal generated by g1 and g2. So in general, and Ahmedi, Aaron, and I, we show that the special fiber of this particular I sub n minus 1, this particular A, is isomorphic as graded algebra to the Orlik-Terao algebra. So Orlik-Terao algebra has an interesting story. It wants to be the commutative algebraic analog of the Orlik-Solomon algebra, which is a cohomology ring of the hyperplane arrangement. So that one has a very important, crucial meaning. Also, Orlik-Terao algebra became very important in the field. It's also known as the algebra of the reciprocal planes and so forth. So, and we see this nice connection between that gadget coming from a hyperplane arrangement field and the special fibers of ideal generated by A-fold products of linear forms. So Ricardo, you and I, we are looking at what's happening if we move to n-2-fold products. And for easy calculation, we took K to be 3. And there is a canonical way to obtain these generators of this ideal, of the special fiber of this ideal, from the even degree elements of the Ehrlich-Terao ideal. So, so we take the standard generators, will be F divided by Li Lj. We associate a new variable Zij. And whenever we have an element of the Ehrlich-Terao ideal, the one that we saw before, of even degree, we pair the variables Yj to get Zij. So G1, yes, G1 is right here. So this can be will get assigned Z24 minus Z14 minus Z12, right? So that's one element of the special fiber of I sub 5 minus 2, right? Now G2 we multiply with this monomial, we get another even degree generator element, and we get these generators for our special fiber. We also have some redundant quadratic generators, and that's all.